You're playing poker with a friend, Texas Hold'em. The last card has been dealt, and your hand's looking pretty good. You have a straight. However, given the cards on the table, there is a slight chance that your friend could have a flush, and that would beat your straight. In fact, the only way that she'd beat you is if she had that flush. If you're unfamiliar with poker, that's okay. All you need to know is that you're pretty sure you're going to win this hand. In fact, you can be more specific about it. When you compute the probability that she has a flush, it works out in this case to be 4.5%. I've gone ahead and put up on the screen the counting argument that gets you that number for any curious viewers that want to pause and think about it. Basically, it just involves counting the number of hands with 2 hearts divided by the number of hands that she can have in total. But all you need to have in your mind for what's coming is that there is a 4.5% chance that she has the flush that will beat you and a 95.5% chance that she does not. And notice how we're visualizing the space of possibilities here. It's this 1x1 square where the top slice of 0.045 units of area represent the possibility that she has a flush, and the dominant 0.955 units of area represent the more plausible world where she doesn't have it. But now she places a high bet, a very high bet. How does this change your belief about whether or not she has the flush? This right here is what Bayes' rule is all about. Updating your beliefs, what's fancifully called your prior distribution, based on new information. Intuitively, after seeing her high bet, we all get that little voice in our head, the one that says, maybe she actually does have a flush. And this very natural feeling, that 4.5% suddenly feels a little bit low given the new information, that's what it feels like to have your gut tell you that Bayes' rule is needed. Now, despite the fact that Bayes' rule is probably the most important formula in probability, it has this strange tendency not to stick in your memory when you first learn it. So what we'll focus on is the right way to visualize what's happening, because if you can remember the visual, the formula itself actually pops out pretty easily. Step 1 is to draw out how the information about the size of her bet fits into our diagram. In the case where she does have a flush, you might estimate that there's a 97% chance that she would place the high bet. Shrewd poker player that she is, she'd know that her flush is the best hand, and the only way she might lose would be in the very unlikely circumstance that you also had a flush, just with higher cards. On the other hand, maybe she's bluffing, or maybe she does have a good hand, enough to make her bet high, but it just wouldn't beat your straight. Let's say that you estimate the probability she would bet this high, given that she does not have the flush, is, say, 30%. Notice, there's a lot of apparent subjectivity baked into these two conditional probabilities, especially that second one. Each one of them depends a lot on your knowledge of your friend and the kind of poker player that she is. It would be nice if there was some clear-cut counting argument, like the prior probability for that flush. But this is actually more representative of most of the probabilities you run into in the real world. They're fuzzier beliefs based on uncertainty. In fact, if you wanted to be systematic about it, each of these is a belief that you would want to be updating throughout the game as you gain new information about how she plays poker. This is an idea that we're going to return back to in a following video, where you have multiple different beliefs, all dependent on each other, and all of which should be constantly updated as you make more and more observations. Right now, though, while we're just building up the simple machinery for what updating a single belief looks like, we'll just move forward with these estimates as they are. A 97% chance that she would bet high with a flush, and a 30% chance that she would bet high without one. With all of this in the diagram, the fact that she bets high means that our space of possibilities is now restricted. It's restricted to this portion that includes a high bet. So the probability that she has a flush, given that she bet high, is going to be the area of this upper slice, the probability that she has a flush and bet high, divided by the total area of that new restricted space of possibilities, the total probability that she places a high bet. One thing I like to do is to imagine reshaping each of these rectangles so that their widths match up, and so that the sum of their heights is still 1, but without changing the area of either one. This way, the probability of a flush, given the high bet, the proportion of the full area of this restricted space that comes from that first rectangle, is given by this height right here. And now, comparing the left and the right, it gives you a sense at a glance for how the prior belief of her flush compares to your new belief after gaining that new information. And this new belief, the probability that she has a flush given that she bet high, is commonly called the posterior probability, or just posterior for short. And before computing that posterior, let's just get a feel for how it behaves by tweaking the various amounts. For example, if you actually think that your friend is risk averse and she doesn't really bluff, then intuitively, doesn't that make it seem all the more surprising that she would bet high? Visually, lowering the probability that she would place a high bet given that she has no flush shrinks the total restricted space of possibilities. And what that does is it increases the posterior, since the proportion that we care about, that she has a flush and bet high, takes up a larger and larger portion of the space of possibilities. On the other hand, imagine that even if she did have a flush, the probability that she would place a high bet isn't all that large. Well, that would decrease your belief that she has a flush. And of course, increasing the prior that she has a flush, maybe because you've been counting cards and you haven't seen many hearts up to this point, well, that would increase the posterior probability. All right, so let's actually compute this guy. The area of that top rectangle is 0.045 times 0.97, the probability of a flush times the probability of a high bet given that flush. The bottom rectangle has an area of 0.955 times 0.3, the probability of no flush times the probability of a high bet given that lack of a flush. Now, our new belief that she has a flush, given that she bet high, the area of the upper rectangle divided by the total area of both put together, actually works out to be 0.13, or 13%. So you still think that she probably doesn't have a flush, but the plausibility that you give to that flush is about 3 times as much as it was before she placed that bet. This whole line of reasoning here is extremely useful and extremely general when it comes to updating probabilistic beliefs based on new information. And the final result we got is called Bayes' rule, or Bayes' theorem. What it says is that to update your prior belief, you multiply it by the probability of seeing the new information given that what you believe is true, in this case meaning the probability of a high bet given a flush, divided by the probability of that new information, which very often breaks down into the sum of multiple parts. Like I said, that new probability you get is called the posterior, and if you ever hear someone use the word likelihood in the context of Bayes' rule, what they're referring to is the probability of seeing that new information assuming the belief is true. Personally, I think that's kind of confusing, since in day-to-day speech we use the word likelihood and probability kind of interchangeably. So why should this term, and not others, be called the likelihood? I don't know, but it's the standard. Like I said at the start, this formula, it has a tendency not to stick. So if I were you, I wouldn't try to memorize it directly. Instead, as you come across new problems, just always think through what the space of possibilities actually looks like, and exactly how your new information restricts that space. Once you have that clearly in mind, the formula itself is easy enough to find, and after rediscovering it a few times, it will actually stick. Here, let's do one more example. You've decided to pursue your passion and become a musician, but you're worried that your music might, well, actually suck without you recognizing it. In fact, as a prior distribution, let's say you place the chances at 80% that your music sucks and 20% that it doesn't. You acknowledge that most people aren't as good as they think they are, but you do have some confidence in your abilities. So, to gather data on the matter, what you decide to do is record a sample track and share it with some of your friends to see what they think. In the case where your music doesn't suck, you give a 99% chance to the fact that you'd get positive feedback. I mean, unless your friends are sadistic jerks, which you only give a 1% chance to, they would tell you it's good if it's actually good. But what if your music does suck? Well, your friends are nice, and nobody wants to shatter your dreams, so in all likelihood, they would come up with something nice to say. So maybe you give it a 90% chance that you would still get positive feedback even if the music isn't that great. So, when you share the track and you get a good review, how does this change your belief? As before, this new information restricts the space of possibilities to this highlighted region, everything that includes some positive feedback. And again, I like to visualize that posterior distribution By resizing each of these rectangles so that their widths match up and their total height adds up to 1, but without changing the area of either one of them. That upper rectangle, it has an area of 0.8 times 0.9. The prior that you do suck times the probability that you'd get positive feedback even given that suckiness. That lower rectangle, it has an area of 0.2 times 0.99. The prior that you don't suck times the probability that you would get the positive feedback that you deserve. So, with that in hand, the probability that your music sucks despite the positive feedback is the proportion of this total area of the restricted positive review space occupied by that top rectangle. That ratio works out to be 0.78, meaning that your belief that the music is bad has only decreased from 80% to 78%. And that's pretty intuitive. If your friends are likely to give you a thumbs up no matter what, how much are you really going to learn from their feedback? In fact, you can actually see here how the more honest your friends are if you do suck, in the sense of reducing the probability of positive feedback in that case, the more dramatically a positive review would decrease your belief that the music is bad. A thumbs up from an honest friend means a lot more. Interestingly though, look at what happens when you get negative feedback, meaning we're restricting ourselves to this other portion of the event space. Because the probability that you get negative feedback if your music is actually good is so very low, almost all of this negative feedback event space is occupied by that region of bad music that gets a negative review. Specifically, the probability of bad music given a bad review works out to be 98%. So in that case, your belief system actually changes a lot as you go from prior to posterior, increasing from an 80% chance that your music sucks up to a 98%. And again, I think that lines up pretty well with intuition. When you get that thumbs down from your friends, especially given how likely you thought it was that they would give you a thumbs up in either case, it really evokes that feeling of, oh, this must not be good. You can imagine how useful Bayes' rule is for things like machine learning and scientific inference. It takes something that human intuition seems to do naturally, changing levels of confidence based on new information, and it makes it mathematical. That said, there is a classic example of how an application of Bayes' rule seems to go totally against what our intuition would say. And in the next video, I'm going to share some thoughts on that example and where it does and doesn't seem to align with our natural judgments. After that, I'll be talking about these things called Bayesian networks. They give you an elegant way to organize a large system of beliefs that all have to update each other based on new information. They are directly relevant to anyone interested in machine learning, but even outside of that, they're just a nice conceptual framework for what a Bayesian understanding of the world looks like.